Hey guys, welcome back to another round of chemistry notes. In this video, we are going to talk about valence shell electron pair repulsion theory. So valence shell electron pair repulsion is a lot of words. We tend to just abbreviate it to the acronym Vsepr, and even that is a little too much work. So we tend to say it like it's a word. We pronounce it Vsepr, which I realize is not how it is spelled, but that is how we say it. So we're going to talk about Vsepr theory, which predicts the geometry or the shape of different molecules. This comes from the fact that electrons surrounding an atom will repel each other, right? All electrons have negative charge, and negative charges repel each other. So if you have your central atom here in the center, and it's bonded here to this atom, and to this atom, and to this atom, then the electrons in this bond and the electrons in this bond and the electrons in this bond are all pushing each other away. You've got repulsion here and here and here, all pushing each other as far away from each other as they can get. So the electrons surrounding that central atom will adopt a shape to minimize that repulsion by arranging themselves as far as possible from each other. Right, the farther apart they get, the less that force of repulsion is, right? We talked about Coulomb's law, and as distance increases, energy decreases. So if those electrons can get as far apart from each other as they can, that force, that energy of repulsion goes down. When we're looking at this, we're going to treat double and triple bonds exactly the same as we treat single bonds. We're going to treat them as one region of electron density. Same as we're going to treat our single bonds. We are not going to treat lone pairs the same. Lone pairs repel more than bonding pairs. We'll talk about what that means here in just a little bit. Just keep it in your brain. Lone pairs repel more than bonding pairs, but all bonds we treat exactly the same. All right, there are two types of geometries we need to learn about. There is electron geometry, which describes the arrangement of electron domains or regions of high electron density. Just the places around your central atom that you can find electrons, be those bonds or lone pairs, those are electron domains. Your electron geometry is determined by the total number of electron domains. So it's determined by all the different places you can find electrons. For our purposes here in electron geometry, single bonds, double bonds, triple bonds, and lone pairs all act the same. They all count as only one electron domain. So a second ago we said that lone pairs are a little bit different. That is going to come into play later. For electron geometry, single, double, triple bonds, and lone pairs are all exactly the same. Molecular geometry, on the other hand, this is where we're going to look at the differences between lone pairs and bonds. Your molecular geometry describes the arrangement of all the atoms around the central atom. Notice it says atoms, not electron groups. This is determined by the number of bonding pairs. This does not include the lone pairs. This is just the bonding pairs. So again, for our purposes here, single, double, and triple bonds are each going to count as only one domain, but here we are not going to factor lone pairs in the same way. They're still going to have an effect. They're just not going to have the same effect as our bonding pairs. So let's start by practicing counting our electron domains, bonding domains, lone pairs, telling the difference, because once we do this, then we'll be able to actually look at our different geometries. Right, so letter A here gives us ammonia, right? NH3 is ammonia, or as you should be able to name it, nitrogen trihydride. So for electron domains, we've got a bond here, that's an electron domain, and a bond here, that's an electron domain, and a bond here, that's an electron domain, and this lone pair, that's an electron domain. Every time you've got electrons touching your central atom, so here, 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 and here, these are all touching the central atom, That's an electron domain. We have 4 electron domains. Bonding domains are electron domains that are also bonds. This includes everything that's not a lone pair. So this will not count for a bonding domain, but this one, and this one will. So we have 4 electron domains and 3 bonding domains. Looking at letter B here, we'll start with electron domains. That's everything touching the central atom. So we've got a lone pair, that's an electron domain, and a lone pair, that's an electron domain, and a bond, that's an electron domain, and a bond, that's an electron domain. We have 4 electron domains. However, for bonding domains, we are not going to count this lone pair because it's not a bond, and we're not going to count this lone pair because it's not a bond. So we have 2 bonding domains. 4 electron domains, only 2 of them are bonding domains. And last but not least, letter C here, we've got a bond here, and a bond here, and a bond here. Yes, this is a triple bond, but remember, double, single, and triple bonds we all treat the same way. So this double bond, we're still just treating as 1 single electron domain, and we have 3 electron domains. As far as bonding domains, there are no lone pairs on the central atom. This is always with respect to the central atom. So we have no lone pairs on our central atom. We have 1, 2, 3 bonding domains on the central atom. Okay, let's take this now, our knowledge of electron domains and bonding domains, and apply it to our different geometries. This table in your notes, you are going to need to memorize the geometries and the bond angles that are listed on this chart, but it's not as bad as it seems. All right, so breaking this down a little bit, we've got a number of electron groups. We've got a number of bonding groups and lone pairs. These kind of go together. We've got our 2 different types of geometries, and we've got our approximate bond angles. So if you've got a central atom with 2 atoms bonded to it, so 2 electron groups, those electron groups are going to position themselves as far apart from each other as they can get, opposite sides of your central atom. As you should have learned in geometry, if you've got essentially a straight line here, that's a 180-degree angle. So if you have 2 electron groups, they're always going to both be bonding groups. So you're not going to have any lone pairs. That'll be linear because it makes a line. Since we have no lone pairs, our electron geometry, the arrangement of the electron groups, is going to be the same as our molecular geometry, the arrangement of the atoms. And since we know these are going to be as far apart as possible, that's going to be a 180-degree bond angle. That's for 2 electron groups. The next section of our chart is for 3 electron groups. There are 2 different scenarios here. If you have 3 electron groups and they are all 3 bonding groups, that's going to give you a trigonal planar geometry. They're going to arrange themselves as far apart from each other as they can get, which is going to be 120 degrees. Right, because our 360-degree circle we have to work with, split up into 3 pieces, gives us 120 degrees each. That's if they are all bonding groups. If one of them is a lone pair, that's going to have a slightly different effect. That's still 1, 2, 3 electron groups, so the electron geometry is still trigonal planar. But now if we're looking at just the atoms, they make this line, but it's not a straight line, it's a bent line. So if you have 2 atoms bonded and 1 lone pair on your central atom, that gives you a bent molecular geometry. And since this lone pair right here, we said earlier, is better at repelling, it's stronger, it's going to push these bonds down a little farther. This lone pair here can push these down stronger because it's more repulsive, which means this angle right here is going to get smaller. So rather than being 120 degrees, it's going to be slightly less than 120. You don't have to know the exact number. You just need to know it's going to be less than 120 because this angle is getting smaller as a result of this lone pair. We are generally going to talk more about molecular geometry than electron geometry. So if you just see what is the shape of this molecule, it means the molecular geometry. These are the names you're going to care a little bit more about. All right, let's talk about 4 electron groups. If you have 4 electron groups, doesn't matter what kind, the electron geometry will be tetrahedral, right? We learned during covalent naming that tetra means 4. So if you have 4 electron groups, it's going to be tetrahedral. As we start changing out bonding groups for lone pairs, the molecular geometry will change. So if all 4 of our electron groups are bonding groups, our molecular geometry is also tetrahedral. This right here, this 109.5 degree bond angle, this is the only one you cannot just figure out using geometry. This is the one you got to memorize. Tetrahedral is 109.5. And it's because now we're taking up 3-dimensional space. So we've got sort of 3 little tripod legs sticking out on our molecule and one sticking straight up. And every angle here is going to be that 109.5 degree angle. That is when it's perfectly tetrahedral. If we take away one bond and replace it with a lone pair, our shape now becomes trigonal pyramidal because we've still got the 3 little legs. So that's trigonal, right? Tri, 3. But instead of being flat, being planar like it was up here, it's standing up a little bit like a pyramid. We can sort of connect these dots and it'll make us a little pyramid. And it's standing up because this lone pair is forcing these other bonds down. It's forcing them away. So then our bond angle, instead of being 109.5, is going to be a little less than 109.5. You do not need to know the exact number. You just need to know that the bond angle is smaller because our terminal atoms down here are being forced closer together. And then, last but not least, we take away another bond. We replace a second bond with a lone pair. So now we've got 2 bonds, 2 lone pairs, and now we are back to having sort of a bent shape. We only have 2 bonds, so they're going to point sort of down. We've got our 2 lone pairs up here. This is the shape of water, so this is a pretty common one to see. But notice that our bond angle here, because it's coming from 4 electron groups, is less than 109.5. Up here it was less than 120. So even though these are both bent molecules, they have different bond angles, and you're going to have to keep track of this. If it comes from 3 electron groups, your bent molecule has a bond angle of less than 120. If it comes from a tetrahedral molecule, your bond angle is less than 109.5. Again, that's caused by the increased repulsion of these lone pairs here. All right, from here it gets simpler. If you have 5 electron groups, you only need to know about them being bonding groups. We're not going to talk about the weird shapes that happen when you start swapping out for lone pairs. If you have 5 electron groups, they're going to be bonding groups. That's what you need to know shapes for. The name for this shape is trigonal bipyramidal. And it's called this because if you look at the shape here, we can sort of connect all these dots. And it's going to make us, I'm a really good artist. There we go. It's going to make us sort of a pyramid up here. And if we connect them on the bottom as well, it's going to make us another pyramid on the bottom. So we have 2 pyramids, bipyramidal, and they are 3-sided pyramids. 1, 2, 3. So that's going to be trigonal bipyramidal. This shape's a little funny because you need 2 bond angles to remember. So your equatorial atoms, like these right here, are equatorial, and the angle between them is 120 degrees. This here is an axial atom, and from here to one of the equatorial, that's a 90-degree angle. So for this, you need to know the two bond angles, but you don't need to know anything about lone pairs. If there are 5 electron groups, they are bonding groups, it's trigonal bipyramidal. You need to know your bond angles. Last but not least, 6 electron groups. This one's a little funny, tends to throw people. If it has 6 electron groups and they are all bonding groups, it is octahedral. Octa means 8, we have 6 bonding groups, but hedral means faces. So up here on our tetrahedral molecule, if we wanted to connect all of these dots, we would end up with a 4-sided figure. It's really easy to see on my beautiful artwork. We have a side here and a side here and a bottom and a back. That's 4 faces to this shape. Same thing here with our octahedral molecule. This is going to go really well. We can connect these 3 atoms to get a face, and we'll connect these 3 in the back to get a face, and these 3 on the right to get a face, and these 3 in the front to get a face. So those are 4 faces making sort of a pyramid here on the top, and then on the bottom as well. If we connect these 3, get a face, these 3, get a face, these 3, get a face, and these 3 in the back will get a face. So really not great, not super easy to tell in this drawing, but what we have is a total of 8 triangular faces on the sides of this molecule, sort of like a crystal shape. And since it has 8 faces, we call it octahedral. And here, the bond angle is really easy. We've got 4 atoms around the equatorial center of our molecule. So if we look at this from the top, we've got our central atom with its 1, 2, 3, 4 terminal atoms. So each of these is a 90-degree angle, looking at it from the top. And then looking at it from the side, we can tell that from here to here, that's also a 90-degree angle. So octahedral has 6 bonding groups, 90-degree angles on each of them. At this point, it's sort of up to you the best way to memorize this. If you are a flashcard memorization kind of person, maybe your best bet is to just put these on flashcards and memorize them. Personally, I think it makes more sense to actually memorize the patterns and the structures. If you have 3 bonding groups and take 1 away, it's still kind of trigonal planar, just squished down a little bit more, and now it's bent. But whatever makes sense to you, go with that. We're going to do a little practice with it now. All right, we got some examples here. First thing we need to do for each is draw the Lewis dot structure, observe whether we're violating the octet rule, and then fill in the electron domains, electron geometry, bonding domains, and Vsepr shape. That's all. All right, so for pH3, phosphorus trihydride, we'll put phosphorus in the center with its 5 valence electrons, and we will surround it with our 3 hydrogens, each having their 1 valence electron. And then we'll connect the dots here, and here, and here. That's going to be our Lewis structure here for pH3. Let's check for elements violating the octet rule. Phosphorus here has 2, 4, 6, 8 electrons, so that's all set. Each hydrogen only has 2 electrons, and that is a violation of the octet rule, that each hydrogen only has 2 electrons. But that's okay. It might be a violation, but it's one we expect. It's one that should be there. And in fact, if hydrogen had anything other than 2 electrons, that would be a problem. So hydrogen does violate the octet rule, but in a way that's okay. For electron geometry, we'll count our total electron domains. So we've got a lone pair, and a bond, and a bond, and a bond. So those are 4 electron domains. And if you have 4 electron domains, remember 4 is tetra, the electron geometry is tetrahedral. For bonding domains, we are only going to count the bonds. So this lone pair doesn't count anymore. We have 3 bonding domains, but 4 electron domains. That means we have 1 lone pair. So that means we're starting with kind of a tetrahedral shape, but then changing one of the bonds into a lone pair. We're going to end up with a trigonal pyramidal shape. So we know that our bond angles are going to be a little less than 109.5 because we started tetrahedral, but this lone pair right here is going to push all of these bonds down, decreasing our bond angle, forcing these to be closer together. So tetrahedral electron geometry, trigonal pyramidal molecular geometry because of this one lone pair right here. All right, let's look at our next one. Here we have H2CO. This one we have to figure out what our central atom is going to be because this one is not as cut and dried. We know it can't be hydrogen because hydrogen can never be our central atom. So we've got it down to either carbon or oxygen. And in this case, this is where we need to look at electronegativity. Carbon is less electronegative. It's going to share with other atoms better. So it's going to make a better central atom. So we can put carbon in the middle. We'll put our hydrogens and oxygen around it. Then we can draw our Lewis dot structures with a valence electron here, 2, 3, 4, and then each hydrogen has 1 valence electron. And oxygen has 6 valence electrons. So then we'll connect the dots and we get a bond right here, and a bond right here, bond here, and a bond there. So 2 single bonds to hydrogen and a double bond to oxygen. And again, we'll check on our octet rule. Oxygen here has 2, 4, 6, 8, so that's good. Carbon has 2, 4, 6, 8, so that's good. Each hydrogen, again, only has 2, but that's okay. That is a violation of the octet rule, but it's one we expect. Hydrogen will always violate the octet rule. So then counting our electron domains, we've got a bond and a bond and a bond. Again, this double bond just counts as 1 electron domain. So we have 3 electron domains, giving us a trigonal planar electron geometry. And since they are all bonding groups, we have 3 bonding domains, and therefore our Vsepr shape is also trigonal planar. So notice that if these 2 are the same number, you're going to have the same geometry for both. Put another way, if there are no lone pairs, your geometries will be the same. If you do have lone pairs, your geometries will be different. The lone pairs are what cause the change. All right, one more example together here. We have BF3. So we'll draw our Lewis dot structure. We only have 1 boron and 3 fluorines, so we'll put boron in the center with its 3 valence electrons. We'll surround it with our 3 fluorines, each having 7 valence electrons. And then we'll connect the dots, and we'll get a bond here, and a bond here, and a bond here. So violations to the octet rule, each fluorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, just like we would expect. Boron, on the other hand, only has these 3 bonds. It only has 2, 4, 6 electrons. But again, that's okay. Boron is one of the elements that will always violate the octet rule. Hydrogen will always have 2, boron will always have 6, and beryllium, when it's forming covalent bonds, because remember, beryllium's kind of a weird one, will always have 4 electrons. All right, so then let's count up our electron domains here. We've got a bond, and a bond, and a bond. Those are 3 electron domains. So our electron geometry is trigonal, planar. And then because these are all bonding domains, we have 3 bonding domains, and our Vsepr shape is also trigonal planar. So again, we have that bond angle of 120 degrees. Exactly. So keep in mind that we had a double bond here giving us a trigonal planar shape. Here we have no double bond, but since they are treated exactly the same, we still have that trigonal planar shape. All right, next you've got some practice in your book. Go ahead, practice those. Keep an eye out for your exceptions to the octet rule, and when you're ready to check your work, the answer key is posted on my website. If you've done all of those and you're feeling good, we have one more thing to talk about in this video, so go ahead and move on, and we will talk about predicting polarity. We learned about polarity in the last video, and you can actually use Vsepr as a shortcut to predict whether a molecule will be polar or nonpolar, because there are certain shapes that will always be polar. These are the shapes that contain lone pairs. So your bent and trigonal pyramidal shapes will always be polar. Let's do some examples. All right, we've got 2 examples here. We are going to draw the Lewis structure for each compound. We're going to determine its molecular geometry, and we're going to give an approximate bond angle between the terminal atoms. And then we'll decide whether the molecule itself is polar or nonpolar. That's all. That's all we got to do. Let's go ahead and get started. Our first one here, NH3, again, this is good old ammonia, or nitrogen trihydride, as you should be able to call it. Nitrogen is going to be our central atom, and it's got its 5 valence electrons. Then we have our 3 hydrogens, each with their 1 valence electron. And then we'll connect the dots. So we have 3 bonding domains and 1 lone pair. So we can sort of work backwards on the shape. This has a tetrahedral electron geometry. But because we've got this 1 lone pair here, it becomes trigonal pyramidal for the molecular shape. And since it would have been that 109.5 had it been tetrahedral, this lone pair is pushing these bonds down just a little bit, pushing them away. So we're going to have a slightly less than 109.5 degree angle. And now we should ask ourselves, is this molecule polar? Well, we said on the last slide, if it is trigonal pyramidal, it will always be polar. This shape is trigonal pyramidal, it will always be polar. And this throws back to what we learned when we first started talking about polarity, which is if you have a lone pair on your central atom, you're going to have a polar molecule. We can draw the dipole here. Remember, the dipole is that arrow that shows the positive side and the negative side of your molecule. You can also use deltas. So if we were going to draw our dipole, we would point it in the direction of our lone pair, because this side of our molecule up here is more negative, where the lone pair is, because these sort of act more negative than a bonding pair. And this bottom part of our molecule, where all the hydrogens are, that's going to be our positive end. So if we wanted to use our deltas, we would do partially negative up here, partially positive down here. On to the next one. All right, next we have NH4. This is your ammonium ion. We're going to draw it pretty much the same way. We'll put nitrogen in the center. But now we've got this plus here. Remember, this plus means that we are going to lose 1 electron, And any time that you are messing with your number of electrons, gaining electrons, losing electrons, it'll always be from the central atom. So since nitrogen started with 5, but we are losing 1 electron, we're only going to give nitrogen 4 valence electrons to work with here. And then we'll draw our 4 hydrogens, each with its 1 valence electron. And then we'll connect our dots, and we get a bond, and a bond, and a bond, and a bond. Remember, when you draw your ions, you need to put them in brackets and give it a charge to say, do you see this thing right here? I messed with its electrons. I took 1 away. And now we have 4 electron domains. They are all bonding groups. This is a tetrahedral molecule. Since it is tetrahedral, the bond angle is exactly 109.5. There's no increased repulsion from any lone pairs. And this molecule is completely symmetrical. Yes, each of these bonds is a polar bond, but they're all pointing opposite directions. They're all canceling out, and this is a nonpolar molecule. By getting rid of that lone pair and replacing it with a hydrogen bonded to our central atom, we've now caused this molecule to be nonpolar. Let's see a couple more examples. Next, we've got good old H2O. So we can put our oxygen in the center with its 2, 4, 5, 6 valence electrons, and our 2 hydrogen atoms, each with their 1 valence electron. And then we connect the dots. And it's pretty easy to see from here that this is going to be a bent shape. Remember, if we have 2 bonding pairs and 2 electron groups, that's going to be a bent molecule. You can see it's a bent line. But since this comes from an originally tetrahedral shape, it comes from 4 electron groups, that means it's starting from that 109.5 degree angle. So our bond angle here is not less than 120, it's less than 109.5. There are 2 ways to get a bent molecule. And this molecule is going to be polar because we've got these lone pairs on our central atom. It's going to be way more negative over where the oxygen is, and we can draw our dipole kind of like this. It's more positive where the hydrogens are and more negative up here where the lone pairs are. All right, last example like this. We've got PCl5. Well, phosphorus is the odd man out, so we'll put that as our central atom, and we'll surround it with our 5 chlorines. And our phosphorus has 5 valence electrons. Each chlorine has 7 valence electrons. So then we'll connect the dots here, and we'll connect the dots here. We'll connect the dots here, and now we are left with this lone pair on phosphorus, but it's okay for us to split this. Remember, phosphorus is in the 3rd period, which means phosphorus has d orbitals that it can store extra electrons in. So we can create a bond right here and a bond right here. And now phosphorus is holding 5 bonds. It's holding 10 electrons, but that's okay. It'll just store the extras in its d orbitals. It can have an expanded octet. This is fine. Our molecular geometry, we know now if we have 5 terminal atoms, this is going to be trigonal bipyramidal. Remembering that it makes those 2 pyramids, one on top, one on bottom. So for trigonal bipyramidal molecules, this is where you have 2 bond angles. Our equatorial atoms have an angle of 120 degrees, and our axial atoms have an angle of 90. So we have both bond angles represented here. And this is a polar bond between phosphorus and chlorine, but since we've got a polar bond pointing this way, and this way, and this way, and this way, and this way. When you take into account the three-dimensional shape of this molecule, these are all canceling out, and as a result, we end up with a non-polar molecule. It does contain polar bonds, but they are all symmetrical. All of our terminal atoms are exactly the same. There are no lone pairs on our central atom, so this is a non-polar molecule. Okay, one more example before y'all can practice on your own. All right, here we've got a word problem. It says, explain the following true statement using principles of chemical bonding and molecular structure. Your answer must include references to both substances. You are encouraged to draw Lewis structures where appropriate. So this is the important part that people tend to forget about this, both substances. You got to talk about both of them if you want full points. So here we go. It says the HOH bond angle in H3O plus is larger than the HOH bond angle in H2O. Well, we know this is true, but we have to explain why. So why don't we go ahead and draw the Lewis structures. H3O plus is going to look like this. And H2O, as we just saw, looks like this. So if we look, these both have a tetrahedral electron geometry. They each have 4 electron groups, but this is trigonal pyramidal. This hydronium ion is a trigonal pyramidal molecular geometry. And water here is a bent molecular geometry. So here we only have one lone pair pushing these bonds down, pushing them away and decreasing the bond angle. Here we have 2. So these are much stronger at pushing these bonds away and decreasing this bond angle. So you could say something to the effect of the lone pair in H3O plus does not repel the bonding pairs as strongly as the 2 lone pairs in H2O. You can definitely and should definitely go into more detail than that. There's a more thoroughly written out answer on the keys on my website, but this is the general basis of the idea. Here we have only one lone pair pushing all these bonds closer together. Here we have 2 lone pairs, they kind of look like Princess Leia, pushing these bonds very close together. So these are going to end up way closer together than these over here. All right, at this point, you've got some practice in your book. You should go ahead, work through your 6 Lewis structure practices and your 2 word problem practices and your many multiple choice practices, drawing out Lewis structures where you need to. The key is posted on my website, so go ahead and check those out when you are ready. You are almost done with the material from Unit 6. There's one more video after this over intermolecular forces, and then you are done. So as always, good luck and happy studying.